Hello everyone, this is Anil Limboo, and this is my report on liquid phase epitaxy for session B examination. So, my roll number is 21NS0172, and I'm a student of third semester. So, here are the contents for my presentation. So, these are the topics that I'm going to cover in my presentation. Yeah. So, starting off, what is a thin film? A thin film is a layer of material ranging from fractions of a nanometer to several micrometers in thickness. So basically a thin film is a material which is very small in terms of nanometer or micrometer. So that is thin film. Moving on, here are some of the examples of the thin films. So as you can see, these thin films are used in solar panels, in electronic devices, and obviously in electronic chips and all. It is also used in CDs. You can see the thin films that are used in CDs. So this is an example of those films that are used in various devices. Now moving on. Now we understood thin film. Now let us understood what is the term called film deposition. Film deposition is basically the technology of applying a very thin film of material between a few nanometers to about 100 micrometers or the thickness of a few atoms on a substrate. So it is basically the method of applying or coating thin films on a substrate, which could be anything, which could be a rigid object or like a metal or crystals, anything. So to form layers. So this is a technique which is used to add thin films in substrate. So that is the film deposition. So why do we add thin films in this substrate? Is because it uh, it it helps the component uh, to improve the mechanical, chemical, and other magnetic properties. Like it helps those properties to be better or be effective by adding thin films. Okay. Now moving on, epitaxy. Now we understood that what is thin film, the film deposition. Now let us understand epitaxy. So epitaxy refers to the method of depositing monocrystalline film on a monocrystalline substrate. That deposited film is denoted as epitaxial film or epitaxial layer. Epitaxial films may be grown from gaseous or liquid precursors. The substrate acts as seed crystals. The deposited film takes on a lattice structure and orientation identical to those of the substrate. So basically, epitaxy is also one of the deposition techniques, wherein what we do is we add our epitaxial film or epitaxial layer in a monocrystalline substrate. So this is also one of the deposition techniques, which is usually grown in gaseous or liquid precursors. Okay. Now this is an example of epitaxial frames. As you can see, it is grown above crystals. So these are the epitaxial frames. Okay. So this is a perfect example. Mm, moving on. So this is a little bit of history of epitaxy. So epitaxy was first performed or developed by in 1951 by Gordon Teal and Howard Christensen at Built Lab. Okay, which is now called epitaxial deposition, to grow a thin layer of material on a substrate that continues the underlying crystalline structures. So these were the two scientists which started the this technique or perform the this epitaxial technique for the first time. Okay, the liquid phase epitaxy technique was first developed in 1963. So it was first developed. So these two scientists, these two persons, they initiated this technique, and it was later on developed in 1963. So it has been now as you can see, it has been successfully used to fabricate various types of 3-4 compound semiconductor devices, including injection lasers, LEDs, photo detectors, and so on. Okay. We understood. Now let us understand epitaxial growth. So epitaxy means the growth of a single crystal film on top of a crystalline substrate. Epitaxy is a Greek word, so which was composed in two parts. So namely epi. Means on, and taxi, which means on an ordered arrangement respectively. So it is an ordered arrangement of crystals. So that is what it means by epitaxy. So thus epitaxy refers to ordered arrangement on a submaterials, oriented growth of epilayers on a single crystalline substrate so that the two atomic planes in contact have planar unit cells that match each other. Okay, this is it for the epitaxial growth. Now moving on, types of epitaxial growth. So there are various types of there are four types which are discussed here. So one is homoepitaxy, pseudo-homoepitaxy, heteroepitaxy, and pseudo-heteroepitaxy. So in homoepitaxy, what usually happens is the films and the substrates are the same material. So the films and substrates, they are of same material, and epitaxial grown layers are purer than the substrates and can be doped independently of it. So you can see all the other uh, types of epitaxial growth. Okay, now moving on. Yes, now the applications of epitaxial growth. So obviously epitaxial growth is very much helpful in nanotechnology, in semiconductor fabrication. Okay, we use that and high quality crystal growth to grow layers of pre-doped silicon to deposit organic molecules onto crystalline substrates. So these are the applications for epitaxial growth. Now, the principle of this process is the process of growing a crystal of a particular orientation on top of another crystal where the orientation is determined by the underlying crystal. The creation of various layers in semiconductor wafers, such as those used in integrated circuits, is the typical application for the process. So the basic principle is that what we do is, so the thin films are crystalline thin films. So we coat or we add the crystal on top of another crystal. So this process is basically the epitaxial growth. So this is the basic principle of epitaxial growth. Okay, now introduction. Now we come to our main topic, that is the liquid phase epitaxy. Now we understood epitaxy. Now let us understand what is liquid phase epitaxy. So liquid phase epitaxy is a solution crystal growth techniques for the deposition of crystallographically oriented thin films, thick layers, or discrete crystals on the seeding or template substrate. It is a method to grow semiconductor crystals layers from the melt on solid substrates. So basically LPE is a process where we grow crystals, where we grow like thin films, where we coat or we will add thin films which are generated crystallographically uh, on top of a crystal itself. Okay, so this is a process, or deposition technique used. Okay, so it is one of the deposition techniques. So this is the introduction. Now let's see the principle. How does it work? An LP procedure consists of providing mechanism creating supersaturation of the solution. First we do that, then introduction of substrate platelet, upon within which the precipitation of the solid film from the solution will occur, controlling the morphology, uniformity, and perfection of the epilayer, and removing from the melt that substrates with the epilayer grown on it. So steps B and D are reported for multiple growth where layers of different composition or doping are grown subsequently on the same substrate. So this is the principle. This is the working principle of LP. This is how the LP works. Okay, how functions. The standard techniques. While performing standard techniques, there are many standard techniques like blob results. Okay, so the major ways of doing an LP is tipping, dipping, and slicing. Okay, the growth system explores both the system. Okay, so these are the standard techniques. So this is a diagram of how the LP is performed. Okay, so these are the diagrams, as you can see the figure properly. Now advantages. The advantages of performing LP or LP liquid phase epitaxy are: it provides us better structural and electrical properties. So So obviously it does that, and growth is carried out at lower temperatures, decrease in concentration of both chemical and crystalline defects. Also, the melt is subjected to less chemical contamination from surrounding. The ability to control material thickness and carrier concentration, a possibility to grow PN junction and other multi-layer structures, superior electrical properties due to low defect density. So these are the advantages of LPE. Now let's come to disadvantage. The disadvantage, one of the major disadvantages is the near equilibrium growth condition also account for some crucial shortcomings of LPE, including poor layer thickness control and difficulty in producing layers with sub 0.1 millimeter thickness. Okay, incompatible incompatibility with the growth of many heterostructures due to lattice mismatch or disequilibrium between on underlying signals. So there would be a disequilibrium due to which it would be hard for this process to grow in heterostructures. Okay, so yeah, those are the disadvantages. So this is a system of LP. This is how an LP looks in real life. Okay, now moving on. Future scope. So obviously, Epitaxy provides an essential link between the art and science of crystals growth and manufacturing of devices and circuits with applications in microelectronics, optoelectronics, and photonics. Therefore, continuing expansion of capabilities and the addition of new methods of epitaxy are important. So yeah, obviously, epitaxy is used in um, like electronic devices such as microelectronics, optoelectronics, and all those things. So epitaxy is used to improve the properties of this electronic devices. So it is very important also for the future. Okay, the applications. This technique is used to grow many crystals employed in modern electronics and optoelectronic devices such as gallium arsenide. Okay, so this LPE, particularly speaking, this liquid phase epitaxy is used for modern developing modern equipments like in electronics devices and optoelectronic devices. Okay, for their better properties. Okay, now conclusion. The conclusion that we get is that liquid phase epitaxy is a solution growth process whereby the driving force for crystallization is provided by the slow cloning of a saturated solution consisting of the material to be grown in a suitable solvent while in contact with a single crystal substrate. So this is all about liquid phase epitaxy, and that ends my presentation. Thank you.